Okay. Yeah, before I start, I'd like to say a few more general words. First of all, perhaps this is all ongoing work, so it's very much work in progress and preliminary results. So we hope, of course, to consolidate that within the next few months. But at the moment, it's really a snapshot, and also it's really only selected results from the large activities or manifold activities that go on within CP5. So I'm going to talk today about two things. The first and longer part of my talk would be concerning the selected effects of diversification in agriculture, and I will use some results from our large-scale field trials that we have been able to conduct over the last 2 years. That refers in particular to the early crop development, and I will explain later on why this talk focuses on that particular time. The second and smaller part is then concerning the question how digitalization and robotics in agriculture might help to improve or enhance diversification of cropping systems. And also, I'm very much looking forward to the discussion with you about this particular question. So just as an introduction, if we diversify cropping systems, then there are various possibilities. One of them is intercropping, so the simultaneous growing of more than one crop species in the same field. And you see here a photograph of just 2 different crop species, a legume and a cereal, being very thoroughly interlinked together and certainly very much interacting with each other. And the large body of literature shows that there's actually many different benefits from growing legumes and cereals or other crop combinations in comparison to keeping these crops separate. These benefits include increased grain yield, improved resource use, reduced disease and pest infestation, and also increased yield stability, sometimes also improved weed control. And so I think it's fair to say that intercropping offers many different benefits, and it's almost inconceivable why this is not done more in practice. And I'm certain that this conundrum is going to be also addressed within PhenoRob in the future. So to actually assess the success of intercropping in relation to monocultures or to sole cropping, we've got this very well established feature, the land equivalent ratio, which is defined as the ratio of the area under sole cropping to the area under intercropping that is needed to give equal amounts of yield at the same management level. That is quite a mouthful and maybe even unnecessarily complicated, but if you express it as a formula, it's quite simple. Actually, it's the sum of 2 ratios, the partial land equivalent ratio for one partner and for the other partner, and these partial land equivalent ratios, or PLERs, are just the ratio of the partner in the mixture divided by the partner in the monoculture. So what we would expect if actually nothing happens is that if we grow a substitutive mixture where each partner is sown at half the density of the situation in the sole cropping, then we would actually expect that the PLER values are around 0.5 or 50%. And if we add them up, we would end up with an LER of 1. So everything that is above 1 would indicate that there's an advantage of the mixture in relation to the monocultures. And you can display this in this very frequently used graph, where the 2 PLERs are displayed against each other, so that it's very clear that everything beyond this line has an advantage in the mixture over the monocultures, because the LER is then greater than 1. And also there's an interesting and for this talk very relevant feature that can be shown in this graph, which is the balance basically between the two crops, shown here by the diagonal in the other direction. It shows where the PLER of one partner is equal to the PLER of the other partner. And if you then consider some points, this point here would be disadvantageous because it has an LER, a mixture effect that's below 1. So in this case, it would be more beneficial to grow monocultures. In this case here, there's also like here, there's an undesired dominance of one partner because one PLER is very high and the other one is very low. So what we would actually want to have is a situation where we've got a balance, a nice balance between the two partners. So basically the point is in the middle of the graph and beyond the LER equals 1 line. So, but the problem is, as I've shown in previous talks as well, is that these mixture benefits vary, and this is very nicely expressed in this publication from a meta-analysis concerning the mixture of cereals and legumes, where it could be shown that on average, yes, there's a strong benefit. The median LER is much greater than 1. It's at 1.16, so 16% yield increase, as you could say in a simplified way. But there's also, as you can see here from this histogram, a lot of variation. And if you display it in the way I've just shown in the previous slide, then you can see that there's also a lot of variation in where the points are actually located. You can see here that in cereal legume mixtures, the cloud of points is slightly or relatively strongly moved up and towards the left, which means that the dominant partner is the cereal. So basically suppressing the legume in many cases, which means that we can actually use this information to adapt the management of this. So as I said, on average, we've got a positive yield, but yield effect, but there's a large variability of this effect. And as I've shown in a previous talk here in this round, there are various sources of variation, and this can also be seen here from our own experiments, where we especially can see that the mixture effect is much greater on the organic field than on the conventional field. That might have not only management but also site-specific reasons, but at least it shows that there are very strong influencing factors that can drive the success of such an intercropping situation. So last time when I talked here, I said that I posed the question, when and where is which mixture best? And from there we can take a next step to ask or to phrase up these three aims. We need to understand the mechanisms and the basis for the transferability of results. We also need to make predictions about the performance of the mixture, actually because there are so many variations and the variability is so large. And the last point, which is the most important for this talk, is we would like to make a prediction about the dominance of which partners actually dominating the mixture, because that is something that we would like to avoid, a strong dominance of one partner. And if we can see relatively early in the cropping season already, if dominance is occurring, then we might have relatively strong information about the mechanisms that underlie this. So This is the reason why we focused on crop emergence as basically the first parameter that we gather in the growing season. Basically, what does crop emergence mean? We just count the number of plants. We determine the actual density of the plants that come out and basically have survived. It's not equal to the germination capacity of the crops. A lot of things can go wrong from the plant's point of view until they emerge, as we will also see later on in the results. But it's basically an early measure of density of the crop. So the questions that we posed here in the for this talk is there an effect of mixing on crop emergence? And this is already quite that would actually be quite astonishing, because at that early time there's relatively little time has elapsed for interaction between the two partners. So it would actually be quite surprising to see a strong effect on crop emergence, or to see an effect at all. Because of the potential of competition to be relaxed in mixtures because of niche separation, there could be the hope that there's higher emergence in the mixed crop in relation to the soil crops. And then, to use that as a predictor, we also asked whether any effects on crop emergence would actually carry on through the season. And to be more specific, is competitive balance already determined at that early stage? So just one of the many potential mechanisms that drives mixture effect at that early time would be compensation. So if one partner fails, the other one would take its place. It's shown here in this graph. There's a failing partner, and if they're grown in monocultures, then this partner has completely failed in this let's say section of the plot, in this small section. But here in the other monoculture, there's no failing, but there's density dependent competition. So in some parts, the plants are grown too close together, so that the emerging plant suppresses the emergence of its neighboring plant. But in a mixed situation, this could lead to actually higher emergence in one partner, not the failing partner, but of course the other one, because for the other one, the competition is relaxed. So this is one of the many potential mechanisms that would lie behind effects of mixing on crop emergence. So what is the basis for the data? It was a large intercropping trial with 4 different factors. We had this mixture factor, of course, with 3 levels. We had the fava bean monoculture, spring wheat monoculture, and the substitutive mixture, which means that both partners were grown at 50% of their monoculture density. But we also combined this with a density level at 2 different densities. So we had 120% of a recommended density, or 80% of recommended density. And this was combined with many different combinations of bean and spring wheat genotypes. So in total, 2 different fava bean genotypes and 12 different wheat genotypes. That was then with 4 replicates and double replicates for the sold fava bean, ending up with 320 plots per site. And this was done at in 3 different environments with the 4 replicates each, and the plot size can be seen here. What is important perhaps also is that the partners were actually mixed within the row. That would be relevant for my later discussion as well. So here you can see the different wheat cultivars, and what I show you today refers to 3 different environments: the 2020 trial at Kleinaltendorf, the Wiesengut organic site from 2020, and also the Wiesengut at from last year, from 2021. one. So in total, we have, I think, 960 plots that give the basis for the data. And it has taken quite some time to actually arrange the data in a way that is clear and clean. So we measured quite a lot of response variables, but today I'd like to focus only on crop emergence and biomass. We also had lots of digital imagery taken from drones. RGB data is currently still being evaluated and analyzed. Also, soil mapping is going on, or has been going on, especially on the Wiesengut side, because this is the link to the previous talk. There's also a lot of soil heterogeneity that we hope could be mapped in a way that we will be able to analyze our data later in an even more sophisticated way. So coming to some of the results, what I show you first is from just one of the environments from Klein Altendorf in 2020, the plot of the wheat emergence in the monoculture against the wheat emergence in the mixture. And these orange lines show what we've actually sown. So the low density here at 320 plants or seeds per square meter, and the respective density of the plants in the mixture, which would be half at 160, and the higher density here at 480 and 240. And what you see then in the next slide is where the points actually come to lie, and these dark triangles show the lower density, and the lighter green circles show the higher density. And for both of them, you can see that they are actually a lot lower than what we would expect from what we've sown. So crop emergence, crop establishment was quite poor at that particular site here combination. But it also offered a potential for actual compensation effects within the crop, and we were very curious to see whether there would be any mixture effect under this special condition of relatively low emergence. And also, of course, the question is then, was there any effect of the mixture on the on the crop emergence? And from this figure, it's actually not easy to see, so I've arranged it in a different way, also for the faba bean. So this is the relative emergence, where we divide the emergence in the mixture by the emergence in the monoculture. And you can see from the histograms, also from the statistical tests, that there was no effect in the faba bean, but a relatively strong effect in the wheat. Also quite a lot of variation, but still significant, with an increase of crop emergence by 22%, which I believe is quite large. And this was actually the point where we saw this relatively low overall emergence. And to map that out, I plotted the relative emergence in the mixture, so where 50% would be the expected nothing happens value, the null hypothesis value, against the wheat emergence in the monoculture. So we would expect that at high values of wheat emergence in the monoculture, the relative mixture effect would be low, so close to 0.5. But we see here that especially at the low end of the wheat emergence in the monoculture, we get the higher emergence, relative emergence in the mixture. So basically, there's a compensation effect here, or insurance effect, one could also say. But at the same time, there's no, no effect here for the faba bean. If we go to another environment, there's actually no effect here in Wiesengut 2020 for any of the crops. or any of the densities. So no effect there. And if we go 1 year further on Wiesengut, again, the fava bean, no, actually, it also shows surprisingly a positive effect of relative emergence through the mixture. Only 9% in this case, not the 22 as observed in the wheat before, but also the wheat responded here with a clear and significant, although lower, mixture effect. So that in itself was actually quite surprising to see out of 6 cases, 3 in which there were positive mixture effects on this very early parameter of crop development. And then what I showed last time as well when I talked here in the seminar was this graph where we see the relationship between the partial land equivalent ratios of the bean and the wheat, and can also see that as is known from the literature, the cereal will dominate, but not so strongly at the organic side. And if we go to the grain yield, then this interestingly the whole spread of the points gets a bit closer together. But we can see a more ideal distribution of the points closer to the diagonal and above the LER equals 1 line, so with positive mixture effects in the organic side. But the question then is about the dominance, especially then, can the relative crop emergence in the mixture be used as a predictor of later dominance? And for that, I've mapped out the PLER, the partial land equivalent ratio of the wheat regarding the emergence here. And on the y-axis, I've shown the PLER for the biomass, for the later biomass. So that must be in June. And what you can see here is that indeed there's a relationship. So in the cases where a positive and significant relationship, so in the cases where the emergence was dominated, in the cases where the wheat PLER, the relationship between the mixture and the monoculture was more positive at emergence, it was also more positive in the biomass. So there's obviously a carry-on, a history or legacy effect going on. And you can also plot this in perhaps a bit more clearer way by calculating the ratio of the PLER of the wheat and the PLER of the bean. So that basically shows on which side of the diagonal the mixture comes to lie. So which one is dominating? So if this number is high, it means that wheat dominates the mixture. And we can see here, so 1 would be the ideal value for no partner dominating the mixture. You can see here that most of the points lie beyond 1 for emergence. But this dominance of wheat at heading or at the later biomass measurement is much stronger, but also positively related to the dominance at emergence. So there are quite interesting results, I think, because they show us that there's at the later stage, we can refer that back to the early, it's already basically partly visible at emergence, and then this dominates of the already dominating partner increases over time. So as can be seen here, the dominance of the wheat staying constant over time would be represented by points on this line, and you can see here that all the points are going up. So it means that the dominance of the wheat is much stronger later on. Okay, so that brings me to the to some of the work that Lucas Drees has has been doing, also trying to predict the biomass ratio now from not from the actual emergence counts, but from RGB drone images. And as can be seen here from the comparison of the different maps, there's quite a bit of good agreement here between observed and predicted biomass ratio. But there might be also, let's say, more advanced methods necessary to actually, let's say there's a potential then to use these images for instant segmentation, so that we actually can count the number of plants and for the whole plot level, and therefore making it possible to have an even more accurate measurement of crop emergence for the whole plot. So with that, I'd like to come to the second part of my talk and deal with the question how and in which ways digitalization and robotics in agriculture may help with such diversification. And what I've shown you before is mostly relating to basically partners mixed within the same row, very close interaction of the two partners, and also being sown at the same time and harvested at the same time. But there are also other forms of intercropping and diversification. In space, you could go from these from mixed within the row to stripes or strips, where you can imagine that the intensity of the interaction increases with this direction, but you can also consider that in time. So in this case, where the intensity of the interaction is lower, you would have partly overlapping partners. So you sow one partner much later than the other and may also harvest them at different times. Or the case which has been done in the CP5 trials, we do the simultaneous sowing and harvesting. And the question, the interesting question now is, which of these systems from an ecological point of view would be optimal, especially if you consider that at least in temperate climates in industrialized countries, as in Germany, you would find that most intercropping, if it's done at all, is done with simultaneous sowing and harvesting, because there are, and also mixed within the row, because there are technical difficulties of establishing other potential intercropping designs. So what helps to answer the question which system is actually optimal is this study, this very recently published study, which looked at different intercropping systems around the world, and it showed that the actual mixture effect was surprisingly not better in the systems where the different partners were interacting most closely, which also might be justifiable. No, it was the other way around. The strips actually showed the greatest mixture effects. And I also did various comparisons looking at different mixture designs with different factors, where they also showed here the temporal differentiation also was related to the mixture effect. So that basically means the lack of overlap. So if it's simultaneously grown, then the mixture effect is lower than if there's a temporal differentiation by sowing the different partners at different times. And also that might be easily explained because the competition between the partners is then reduced. But what you can also see here in the picture is that usual farm machinery used in Europe might not be compatible with such such strip systems, because you have to harvest and manage the crops on the strip level, you would need, let's say, small-scale machinery. And there you can see that someone is actually still driving this machine, but from there it's also only a small step to basically have a small-scale robot that autonomously manages this intercropping. So the aim here would be for, so if we take this these results from this review, then we could say which technique actually enables more flexibility in terms of the spatial and temporal cropping design. So what we would need would be robots or small intelligent machines that could autonomously perform sowing and management in one or both or even more crops in, for example, narrow strips. Perhaps also which could harvest single partners from the mixture, in which way they would be able to or enable combinations that are maturing at different times. Although I would think that harvesting is still the greater challenge in this case. Also, imagining that one machine would actually do this, all the different tasks required in this intercropping design is also quite challenging to imagine. So this weeding robot here in sugar beet might not be the ideal candidate. We're currently toying with the idea to implement such a small and rather flexible machine to enable us to set up a design of intercropping which is very different from the one which we've tested before, but would only be able to be implemented with such an let's say flexible machine. Okay, with that, I would like to thank you for your attention, and I'm curious to answer your questions. Thank you.